Good afternoon, Nandana. So we'll just wait for another 5 minutes. Okay, so we'll wait for 5 minutes to see if somebody joins, and after that, we shall start today's session. Thank you. Okay, so I believe we can start with today's session then. So this is advanced thermodynamics and combustion. Uh, so this is the second live tutorial session in the series of 13 such sessions that will be conducted in this period of this particular course. Right? So last in the last session, we basically reviewed our basic knowledge of thermodynamics, right? And for this week, the uh, discussion mainly revolves around entropy, right? And maybe in the next week, the Exergy part will be introduced. Okay. So the instructor of this course, as you all know, is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And I am a PhD student, a research scholar, pursuing my PhD under him only. Okay. So these sessions are being conducted under EMRF NPTEL TA-ship scheme. Right? So I am a teaching assistant for these live tutorial sessions. Right? So with this, I believe we can move on to the topics, right, that have been covered in this week's content. Right? Okay. So here in lecture 4, we started with the Clausius theorem, right? So by means of a generalized force and displacement diagram, we discussed Clausius theorem, right? And the main thing that came out of this theorem was that. So we'll briefly discuss the topics covered in this uh, week, right? And after that, we'll move on to questions. Maybe 10 to 15 or 15 to 20 minutes we'll discuss. So the main thing that comes out of this is that for a closed system, right? For a cyclic system, sorry. So is equals to zero. Or so this is the mathematical statement of Clausius theorem. But then we need to keep this in mind that this statement is true for reversible processes or reversible cycle. Though your cycle is it's a cycle, right? But then it has to be reversible. Only then we can apply this particular mathematical statement to that cycle, right? So diagrammatically also this has been discussed in this week's lecture 4, right? Right. And through this Clausius theorem, we moved on to discussions on entropy, right? So we first defined entropy using this dq by t ratio, right? And its integral, right? And then we also discuss that how entropy is a state function, but though the heat transfer is not a state function, it depends on path, but then this entropy is a state function, right? So these discussions were done in this particular topic. And after this topic, we discussed how we can evaluate entropy, right? Mathematically, if we want to evaluate entropy, right, for our system, so in that case, how do we proceed in that case, right? And for that matter, we took an example of ideal guess, right? And we derived two formula, right, for this, right? So in entropy evaluation, for ideal gases, do is we can write this also in this way. So for ideal gas case, we derive these two formulae, right, for the entropy calculation or entropy evaluation. Right? And after this, we moved on to the next topic, that is temperature entropy diagram. Right? So, which is basically TS diagram. So it's a very important diagram, right? And a lot can be deduced based on a TS diagram of a system, right? Thermodynamic system. One thing that we need to remember is that this temperature entropy diagram, the area under this temperature entropy diagram, it gives us the heat transfer, right, for a particular system. And then if we try to draw this temperature entropy diagram, right? So different cases or situations I'll draw, right? So if temperature remains same, so it will be like this, right? And if the entropy remains same, right, isentropic. And then if the volume remains same, and if the pressure remains same, so roughly the diagram will look like this in these cases, right? So this is our temperature entropy diagram. And after that, a very important topic we discussed, that is entropy and reversibility, right? So how these two terms are related, right? So so we saw in this particular topic is that that if the system is reversible, right? In that case, it will have the ability to come to its original state, right? Because it's reversible. So in that case, if the system uh, after going through a particular process comes to its original state, in that case the entropy change for that whole cycle will be zero, right? So I have stated earlier also that this entropy is a state function, right? So if a system moves in particular process and then comes back to its original state, then in that case the uh, entropy in that case for whole the cycle will be zero, right? Entropy change, right? So these discussions were covered in entropy and reversibility, right? And then how irreversibility is linked to entropy. So this we handled in the next topic, right? So various types of irreversibilities we discussed, right? So in that we discussed mainly four irreversibilities, right? So first was external mechanical irreversibility, right? And then there was internal mechanical irreversibility. And after that, there was external thermal irreversibility, right? And the last one was chemical irreversibility. So, comprehensively, the examples of all these cases have been well covered in the lectures, right? So, I'll not go into that, right? So, this discussion was basically done on irreversibility, right? Right. So, in case of irreversibility, we see that if you see for the whole universe, the entropy, right? So this case shows that the entropy for whole universe will always increase in case there is irreversibility in a system, right? So the formulae also have been tabulated for all the cases, examples for different cases that have been discussed in lecture 4. Okay. So at the end, inferences were made based on the discussions done in this particular lecture, right? Based on entropy, based on reversibility, based on irreversibility, right? And what is the linkage between reversibility and entropy, and irreversibility and entropy? All this has been covered in lecture 4, right? And then uh, lecture 5. So in lecture 5, we started with the content of the previous lecture only, right? So we discussed Clausius theorem and second law, right? So as I have written here, right? So all this has been discussed in this particular topic, right? And then after that, so irreversible processes, heat and entropy. So this is a very important topic, right? Heading that has been discussed in this particular lecture, right? So in this case, through an example, we discussed an irreversible process, right? And then by means of that irreversible process, we stated our Clausius inequality, right? So which essentially is So if there is internal irreversibility in a process, right? So this is true for internal irreversibility, right? So in that case, this integral will be less than zero, right? And we also saw that this, right? That for a reversible process, this integral is zero, right? So if we add these two statements, right? So this gives us that in totality, if you see for all the systems, right? Cyclic, right? The process has to be cyclic. So in that case, this integral will always be less than equal to zero, right? So this is our Clausius inequality, right? So this was discussed in this particular topic, right? And after that, we move on to the yes. So after that, also in this heading only, so we have related this heat transfer with the entropy change, right? For the same example that has been discussed. No, sorry, for a different example, right? So in this particular discussion, we came to a conclusion that, so I'll not write the whole derivation, right? But then main thing to take away from the discussion was that for an irreversible process, the entropy change will always be greater than this dq by t. Okay, so this was another discussion under this particular topic, right? Irreversible processes, heat and entropy. And after that, we discuss entropy and non-equilibrium states, where we, by means of an example of a rod which was connected to two reservoirs of uh, different, uh, so two air, yes. So by means of a rod which was connected to two reservoirs, right? One was at high temperature and one was at low temperature. So then we keep this rod in a enclosed adiabatic system, and then we see how this rod initially at non-equilibrium state and reaches its equilibrium state, right? And then how do we define the entropy of this particular example? So this has been discussed in this particular topic, right? And then after that, we moved on to next heading, that was principle of increase of entropy, right? So basically, this principle says that for all the possible processes in this universe, the entropy will always be greater than equal to zero, right? So this is our principle of increase of entropy, right? Right. So this was about lecture 5. And then in lecture 6, we basically discussed the entropy balance related to a closed system, right? And then control volume. So first we briefly discussed the data interpretation of entropy, right? So how do we incorporate entropy data into our thermodynamic discussions, and how do we include the entropy data into our thermodynamic discussions? So this has been discussed in this particular topic, right? And then after that, entropy equations have been discussed in the next topic, right? So entropy equations like right. Okay. So after that, we moved on to the entropy balance for closed system, right? So I'll quickly write the entropy balance for a closed system, and then just one equation, right? So the time rate of change of entropy, right? In case of a closed system. So for so this is like this, right? Where this sigma term is for the entropy production in a system, right? So if there is a change in state of system from one to another, in that case, if there is irreversibility, in that case, this entropy production comes into picture, right? Otherwise, if there is heat transfer across the boundary of a system and its surrounding, in that case, this particular term comes into picture, right? Then, how this entropy affects the directionality of a particular process, right? So in that case, we saw that if there is the all the actual processes that take place in a universe, in that case, if a process has to happen, there should be an increase in entropy only, then that process will be feasible, right? So such discussion we had in this particular topic, right? And then after that, we discussed entropy balance for the control volume, right? So for this, we saw that time rate of change of entropy for control volume can be written as, so here everything in terms of terms, right, will remain same as the previous case, but then there is some addition, and that is these two terms. So because this entropy is an extensive property, so like mass is an extensive property, volume is an extensive property, right? So they depend on the extent of a particular matter, and based on that the value of the property can be defined. In the same way, entropy is also an extensive property, right? And then this first MISI is for when uh, some matter enters into our control volume, right? And then MES is for when some matter exits or some mass exits our control volume. So with that, there is uh, entry of entropy in the control volume and then exit of uh, entropy from the control volume is there. So for to cater that, these two terms have been included in this particular equation, right? Okay. Right. So this was about entropy balance for control volume, right? And then at the end of this lecture, right, we discussed isentropic process, right? So isentropic process basically is uh, that where we have no change in the entropy in a particular process. So delta S in that case will be 0. So how pressure and temperature can be related between two states, right? In an isentropic pressure, and then density and temperature can be related, and then pressure and density can be related. So this has been discussed in this particular topic, right? So such terms also we come across in the study of compressible flows, right? Also. So this was about the topics that were discussed in this particular week, right? So now we will quickly move on to the questions, right? So first of all, as we have been doing in the previous session, so we will first take conceptual questions, and after that we shall take numerical questions, right? So let's see the first conceptual question. So the topic of this question is Clausius theorem and the second law, right? So this question is from lecture 4 only, right? And the question says that the work done in all reversible paths between same states is path dependent. So whether this uh, question or statement is true or false. So this particular statement basically is from your first slide only of the lecture 4, right? So based on this particular statement, then there is a discussion on in that in reversible paths, how for two different paths heat. The discussion on heat has been done. So what happens to heat if there are two different if the states two states remain same, but then there are two different reversible paths. In that case, how heat comes into picture, right? So how heat fares in that case, this has been discussed. So the answer to this question is false, right? So in case we have two states, right? Two thermodynamic states for a particular system, and the paths that are taking this system from one particular state to second state, and if there are two paths that are reversible in nature, in that case the work is mm, not depending upon the path, right? It is independent, right? So this statement in that case will be false, right? All right. So this was our first question. So we'll move on to our next question. So the topic of this particular question is again Clausius theorem and second law. So from this topic only the question has been taken. And this is question number 2, and it says that the Clausius theorem may be stated as the cyclic integral of parameter dq by t is always zero for all the processes. Right. So this is a statement type of question, and we have to tell that whether this particular statement is true or false. Okay. So the statement is about Clausius theorem. Okay, and it says that the cyclic integral, right? So it's when we are dealing with such type of questions, in that case we need to be very critical about all the words that have been given in the statement, right? So the first here is cyclic integral, right? And then parameter dq by t is given, and then is always zero, right? So it's an extreme statement, right? And for all the processes. So we have seen that for Clausius theorem, right, the integral of dq by t is zero for a special case, right? So it is not at all the case that this integral is zero for all the processes, right? The integral by t is zero for a special case, that is reversible process, right? So only if the process is reversible, in that case it will be reversible, and it is not true that the integral is zero for all the cases, right? So this statement comes out to be false in that case, right? Right. So B option is correct. Okay, so the next question is on entropy and the second law, right? And this is question number 3. And it says that entropy change of a system is path dependent. So whether this statement is true or false. Yes, please. So we are at third question of this session, and the question is based on entropy and second law. So it's the statement says that the entropy change of a system is path dependent. So whether this statement is true or false, please try to answer this. Okay. So I have already discussed that entropy is a state function, right? So what do we mean by state function is that it depends on the state of a particular system, right? And not on the path that the system has taken to move from one particular state to uh, another particular state, right? So in that case, the entropy change of a system is a path independent property, right? And the answer to this question comes out to be false, right? Okay. So now moving on to the next question of the session. So this question again is on the topic entropy and second law. Okay. And the question is question number 4, and it states that the entropy change in a reversible process is always zero. So whether this statement is true or false. So please try to answer this question. So I have placed this question here only because when we discuss entropy, at that time we see that for some cases entropy is zero, right? And by mistake, we sometimes connect uh, no change in entropy situation with the reversibility only, plainly reversible. We do not take this into consideration that the process has also to be cyclic, right? So because it's a state function, right? So if it doesn't reach its original state, in that case we cannot directly say that the entropy change for a process is zero, right? In that case there will definitely be process change, right? There will definitely be entropy change. Though that matter is different, that entropy change can be positive, negative, or it can also be zero, correct? For that matter. But then, if you see just the statement only, so it has stated that entropy change in a reversible process, right? So it hasn't told us that this is a cyclic process or something like that. It has plainly said that it's a reversible process. So in that case, it's not necessary that it has to be zero, right? And if it is cyclic and it is reaching its initial state, right, after conducting various processes, in that case, we obviously can say that entropy changes, but not just for a reversible process. We can make this statement. So in that case, this will be a false statement. Okay, so we'll move on to next question then. So this question is on temperature entropy diagram, right? Temperature entropy diagram, this, right? So this is T versus S diagram. And the question here says that a reversible adiabatic process is dash in nature. So four options have been given. So we can try to answer this question. So in the entropy balance discussion, we saw that if there is irreversibility in that case, there will be entropy production, right? But here we in this question we have reversible term in the picture, right? Also, we have adiabatic term, right? So In that case, there will be no heat transfer across the uh, system and the surrounding, right? And if the process is reversible, in that case, it boils down to that the entropy of that system won't change, right? These two conditions make a process isentropic, right? That is, no change in entropy. Okay. So out of the four options, option C will be correct, right? So isotropic is if in all the directions properties remain same, right? Which is the case for gases, right? Also, right. And then other two options, isobaric and choric, do not fall within the meaning of this particular fill in the blank, right? So in that case, C will be correct option. Right. So let's move on to next question. Question number 6. Again, the topic of this question is temperature entropy diagram, and it states that the area under the temperature entropy diagram represents the dash transfer to and from the system. So four options are there. Let's try to answer this question. Okay, so if we see our this TDS diagram, right? If some process is there, right? At some point, let's say we have some temperature T, and then this is ds, right? Infinitesimal entropy change, ds, right? So in that case, the area, right, tds basically is dq, right? Change in the or the heat transfer, right? The area under this tds ts diagram, it gives heat transfer. And then if we want to integrate it for the whole process, maybe if it is going from 1 to 2, right? In that case, we can integrate it, right? And this way we can calculate our heat transfer using a temperature entropy diagram. So out of the four options, option B is correct. So yes, right. So moving on to next question. Next question again is on temperature entropy diagram, right? This is question number 7. And it states that for a reversible isobaric process, the slope of TS diagram is ratio of dash and dash. Okay. So this is fill in the blanks type of question, and we have four options. So in the question, it has been mentioned that first it is reversible and then it is isobaric. Isobaric means the pressure remains same, right? And in the TS diagram, what will its ratio be? It's yes, the slope of TS diagram. What will be the slope of TS diagram for this particular process? So the slope of TS diagram basically is dou T by dou S, right? For any instantaneous state, right, in this process. Because it is isobaric, that is at constant pressure. Dou T by dou S at constant pressure we have to find out. Yes, this is the question. So it's already 4 p.m. So maybe we can take a 5 minutes quick break and then after we can proceed with the remaining part of the session, right? All right. Okay, so we can start with the remaining part of the session, right? So this question was based on temperature entropy diagram, and this is question number 7, and it states that for a reversible isobaric process, the slope of TS diagram. So to solve this particular question, right, and then there are four options have been given to us, right, and the question includes terms like absolute temperature, right, and then specific heat at constant pressure, and then specific heat at constant volume, right? Right. And then these three terms have been shuffled around, and then options have been made. So if we see that how we evaluated our entropy, right? Here, right? So we have given these formulae here, right? But as the question states that the pressure here is not changing, right? So this term will go to zero, right? In that case, we are left with ds cp dt by t, right? And which comes out to be ds by dt equals to cp by t, right? Or dt by ds cp by t, right? And in case we have to write it in this partial differential terms, right? So we can also write it this way. At constant pressure, right, it becomes P by Cp. This is P by Cp, right? So this is the ratio of absolute temperature and specific heat at constant pressure, right? So if you see our options, A option is absolute temperature, and so A option will be correct, right? Okay. So this is the answer to question number 7. So moving on to next question. This question again is on temperature entropy diagram. And this is question number 8, and it states that for a reversible isochoric process, the slope of TS diagram is the ratio of dash and dash. The same way, the options remain same, but then here it has asked for isochoric process, right? And in this scenario, we will write ds as CV ln T plus n r ln, sorry, CV dt by t, and here dv by v, right? So this will be the differential form. In terms of specific heat at constant volume, right? Right. So because the process is isochoric, in that case, this will be 0, right? And then ds dt by t implies dt by ds equals to t by cv, right? Or dou s at constant volume equals to t by cv, right? So if we see our options, so in this case, option B is correct. Okay, so this was our question number 8, right? So B option is the correct statement in this case. So we shall move to the next question now. So the question is on entropy and reversibility. So this is question number 9, and it states that the entropy change for a system can never be negative. So whether this statement is true or false, let's try to answer this question. So the statement first introduces entropy change, right? And then it says that it can never be negative. So whether this is true or false, this we have to tell. So we have discussed this in lecture 4 only, right? So if we suppose that there is a system in which heat is being absorbed reversibly, right? In that case, the entropy change for the system will be positive, right? Because it is receiving heat. But then on the other hand, if you see the reservoir from where the heat is coming into the system, right? So the reservoir has lost heat, right? So in that case, the entropy change for the reservoir will be negative, right? So this has not to be confused with the statement that entropy change for the whole universe is always greater than equal to zero, right? Because in that statement, the entropy we are talking about is of the whole universe, right? But here we are not talking about the whole universe, right? So here we are talking in parts, right? So what happens when a system and its surrounding interact? So in that case, what is the change in entropy for the system and what is the change in entropy for the reservoir? So that we have to take into consideration, right? So in case of heat absorbed by system, right, from some reservoir, the entropy change for reservoir will be negative, and vice versa will be when the heat is uh, rejected by the system, right, to some reservoir. So this statement, if we see that says entropy change for a system can never be negative. So this is a false statement, right? Okay, then moving on to next question. The next question is based on Clausius theorem and second law. It is from lecture number 5, and this is question number 10. And it states that according to Clausius inequality, the integral of dq by t for an irreversible process is always less than 0. Yes, let's try to answer this particular question. Clausius inequality. The question is based on Clausius inequality, right? So, so this is the statement of mathematical statement of Clausius inequality, right? where the integral dq by t, right, closed integral, is always less than equal to 0. If there is internal irreversibility, in that case it is less than 0. If it is there is no irreversibility internal, in that case it will be equal to 0. But the main point as far as this question is concerned is that this is a closed interval integral, right? Which means that this statement holds true only when the process is cyclic, right? So if we take only a discrete process which is irreversible, in that case, this statement might not be true, right? But if we consider the whole cycle in which internal irreversibility is there, in that case, this statement will be true, right? So if we see our statement of the question, it says that integral of uh, dq by t. So just plainly, if the statement writes, in that case, we cannot state that this statement is true. Right? So cyclic word is very important. That must be included if we are discussing process inequality, right? So in that case, this becomes a false statement, right? Had cyclic been there in the statement, it would have been a true statement. But then, because cyclic is missing from the statement, in that case, it is a false statement. So next question is basically a factual question. So if you know it, you know it. If you don't know it, you do not know it, right? So this question is from entropy data interpretation, right? And the question number is 11, and it states that the enthalpy entropy diagram is commonly known as Mollier diagram. So whether this is the correct statement or not. So this is a correct statement. Right? Nothing to discuss in this particular statement. Right? So this will be a true statement. So enthalpy entropy diagram is known as Mollier diagram. So moving on to next question. So next question is based on entropy equations. The entropy equations that I have written here, right? These. And based on these entropy equations, further discussion has also been done in the lecture 5, I believe. Okay. So based on this entropy equations, the question number 12 is as follows. For an incompressible substance, the entropy change depends on, right? So the question asks about entropy change, right? And then also tells that it's an incompressible substance, right? So its volume cannot change, right? So in that case, dV will be 0, right? So the question now is about entropy change, right? And we have to use the entropy equations to answer this question. So please try to look into this question. So if we see our entropy evaluation, right? So this and these equations, all this come under entropy equations only, right? So with the help of these equations, we can evaluate the entropy, right? So in this case, we will again use this formula that we used here, right? In entropy evaluation, right? This is question number 12. This is from lecture 6, right? So, and entropy change can be written as, right? But as there is volume change is 0, so this whole term will vanish. In that case, we are left with ds equals to ct by t, where ct is nothing but specific heat, right? So if we integrate it, it basically becomes in case the specific heat is constant, right? It will become S equals to C. CLNT and constant of integration. So if we see our question, right? So entropy change depends on. So if we see our this derivation, in that case, we can clearly see that it depends on specific heat and then also depends on temperature, right, of the initial and final states. So when we see the options, It depends on pressure only, so pressure is nowhere in our derivation, but temperature is there. But then alone temperature is not there. Specific heat also is there, so which is in option C. Then pressure and specific heat only. Pressure nowhere is there in the question, right? So C option is correct, right? So this is question number 12. Option C is correct, right? So moving on to next question. So this is from entropy balance of closed system, and it says that the this is question number 13, and it says that the entropy production can never be negative. So whether this statement is true or false. So this is our entropy production. So this is for closed system, right? Sigma. So can entropy production be negative? Let's try to answer this question. Okay. So the way entropy production has been defined, right? So in its name also the answer is there, right? So the way the sigma has been defined, right? So it caters to the entropy change when there is irreversibility in the system, right? Or process. And in that case, if there is irreversibility, there will be entropy production in that case, right? Entropy change in the form of entropy production, right, in the system. So the way it has been defined, it has always to be positive. Okay. So either it can be zero if there is no irreversibility, internal irreversibility in the system. But in case if there is such irreversibility, in that case there will be entropy production. Right? So it will always be positive, right? So if it says it is negative, that is not a true statement. In that case, it's a false statement. Sorry. Okay. So moving on to next question of the session. The question again is on entropy balance, sorry, for a closed system. So this is question number 14, and it says that entropy production for a system with no internal irreversibility is finite. Okay. So I've just uh, answered this question, right? So I've just answered this question. So if there is no irreversibility, there is no entropy production. The whole purpose of including the entropy production or sigma in the entropy balance statement is to cater the irreversibility, internal irreversibility in the system. If that is not there in the system, in that case, there will be no entropy production. Okay. So if there is no internal irreversibility, in that case, entropy production is zero. This will be zero. Okay. So this will also be a false statement. So moving on to next question. So we are left with another three conceptual questions. Let's see if we are able to cover those three. Otherwise, then we'll move on to numerical questions. So we have, I believe, four numerical questions. So that might take maybe 10 to 15 minutes, right? So we have time right now. So let's try to complete our conceptual questions. So this is from entropy and directionality of processes. This is question number 15, and it states that the only processes that can occur are those for which the entropy of isolated system increases. So in the discussion of directionality of processes, we uh, understood it by considering isolated system, right? So we isolate the whole system, right? And then the interaction between system and surrounding, we check. And how the entropy fares in that case, this we discussed in this topic, right? So the question says that a process is possible only if the entropy increases for the isolated system. So from our discussion, it is very evident, right, that if a process in actual has to take place, in that case, entropy of the isolated system must increase. Only in that scenario the process is feasible, right? So because it's a statement type of question, so the statement is true in itself, right? So it is a true statement. Okay. So moving on to next question. So this is a true statement. So the question has been formulated from the entropy and control volume discussion of lecture 6, right? And this is question number 16, and it states that entropy is an extensive property. So if you know what is extensive property, then within the context of entropy, we have to tell whether this statement is correct or not. Yes, so I have already discussed this in the topics section of this session. Then you can try to answer this question. So, in the discussion of entropy balance for control volume, entropy balance for control volume, we saw that when there is entry of some mass in the control volume, and when there is exit of some mass out of the control volume, in that case, this entry and exit brings with it uh, entropy also, right? So when there will be entry of some mass, the entropy linked to that mass will also enter the control volume. And when particular mass exits the control volume, in that case, the entropy linked to that mass will also exit the control volume. Okay. So from this discussion, what we uh, infer is that entropy is an extensive property, right? It depends on the extent of the matter, right, for which it is being defined. So if the extent increases, the entropy linked to it will also come into picture, right? So this in that case is a true statement, right? Okay. Okay, so the last question in this section of this session, I believe question number 17. So, So this question is on entropy and control, again on the entropy and control volume topic. And this question is question number 17, and it states that for a control volume at steady state, the time rate of entropy change of the control volume is finite. So whether this is true or false. So from our discussion, we have covered this, and we have seen that if the control volume is in steady state, right, in that case, there will be no entropy change within the control volume, right? If the control volume is in steady state, right? So in that case, if the statement says that the control volume, the time rate of entropy change is finite, in that case, it is a wrong statement, false statement, right? Okay. Okay, so this is it about conceptual questions, right? Or theoretical questions. Then we move on to numerical questions, right? So four numerical questions are there, and we shall try to solve them. So first question in that case is on entropy evolution, and this is question number 18, and it states that a certain chemical reaction takes place simultaneously at 112 degrees Celsius. If the enthalpy change for the reaction is 20.6 kilojoules, what is the minimum value of delta S, that is entropy change for the reaction, right? So we try to solve question number 18. Then S has been asked, right? And what is given is that enthalpy change, right? Enthalpy change for reaction. Change for reaction is 20.6 kilojoules. That is 20600 joules, right? And then it's a spontaneous process which takes place at temperature T equals to 112 degrees Celsius, right? So in Kelvin scale, the temperature will be 273 plus 112, right? Which comes out to be 385, right? And now if we want to calculate delta S, because enthalpy change is 20600, and then temperature at which this takes place is 385. So this will give us the entropy change, and which is Yes. Okay. So this is my answer to question number 18. Right. Then question number 19 is on entropy equations. And this question says that the temperature of an ideal monotonic gas is raised from. Okay. The temperature is being raised of this gas from 10 degrees Celsius to 324 degrees Celsius. And the isentropic condition is being maintained, right? So delta S or ds will be zero. So pressure has increased in that case from P1 to P2. So find P2 by P1, right? So this is based on entropy equation. So we will use entropy equations, one of the entropy equations to solve this, right? So first of all, let's convert the temperatures into Kelvin. So first is 10 degrees Celsius, that will come out to be 283 Kelvin, right? And then another temperature in the question is 324 degrees Celsius, right? And this will come out to be 397 Kelvin, right? And we know delta S is zero because it's an isentropic process, right? Then in the entropy evaluation and also in the entropy equations topic, these two topics, we have seen that change in entropy, right? Entropy equals to NCP, right? ln T2 by T1 minus NR ln T2 by T1. So this we have seen. But this change in entropy here is zero, right? In that case, this statement becomes NCP ln T2 by T1 equals to NR ln T2 by T1. Now, N and N will cancel out. Now we know Cp can be written as 5 by 2R for monoatomic gases, right? In that case, our above statement becomes 5 by 2R ln P2 by T1 equals to R ln P2 by T1, right? Now, R and R will cancel out, and now we will place T2 and T1, right? Before that, what we will do, we will bring 5 by 2 inside ln, right? So doing this, we will be able to eliminate this natural log, right? And this here becomes P2 by P1 equals to T2 by P1 5 by 2, which is which is T2 here is 597, right? 7, and T1 is 283 and 5 by 2. So if we work this out, this comes out to be 6.46, right? So P2 by P1 is, this ratio is 6.46, right? 6.46. So if you see our answer, so this is 6.46, right? So this is question number 19. Now moving on to question number 20. So this is a comprehensive type of question, right? Questions. 20 and 21 questions are comprehensive type of questions. So here the data pertaining to these two questions is as follows: a reversible cyclic. So it is first of all reversible, then it is cyclic, right? Then it is an heat engine, right? So we are getting work from this heat engine. Is embedded in two heat sources. One is a finite body at 750, and then other is a reservoir at 350 Kelvin. Right? And then heat capacity of the body is this, right? Now we have to tell that this is question number 20 based on entropy questions. So this we have to tell that the change in entropy of the body. So we have to calculate the change in, so calculate should have been there, calculate the change in entropy of the body. So two temperatures have been given, and then this specific heat has been given, right? So if we solve this question, right? So delta S for body will be Cp ln T2 by T1, right? Okay, right. So it's a reversible cyclic heat engine. Okay. So in that case, entropy is being given by this formula, right? Cp is given to us at constant pressure, and then two temperatures have also been provided to us, right? All right. So if we place these in this given statement or formula, so T2 is 350 and T1 is 750, right? It is moving from 750 to 350. And if we work this out, it will come out to be 1.048 into minus 0.76, right? And this will become minus 0.8 kilojoule per kg Kelvin, right? So now if you see the sign of this entropy change, this is negative, right? So it means the entropy change for a body is negative. So entropy change can be negative, right? If we see uh, a particular part of the whole system and surrounding, right? So body for body only the entropy is increasing, but if we see the whole universe, right? In that case, the scenario will be different. Right? So this was question number 20, right? Okay. Then there is question number 21. Minus 0.8. Calculate the change in entropy of the heat engine. So because the data on question number 20 and 21 states that it is a cyclic process, right? So in that case, it's a cyclic, reversible cyclic heat engine. In that case, because it is cyclic and entropy is a state function, in that case, the change will be zero. Right? Change will be zero. There will be no change in entropy. Right? So this is about question number 20. Right. And then there were doubts from previous session. Right? So there were basically two doubts from previous session. Right? So I'll just refer, give two references, right? So you can refer to these two. So first was on the example of an internally and externally reversible process, right? So in that case, you can refer to this particular reference. I'm just writing this down. So for this example, you can refer to this particular book, and I have given the page number also where you can find this example. So this example is basically a pendulum in a vacuum. This example is there, right? Where it will be both internally and externally reversible, right? Then there was a doubt on hydrostatic work, right? So whether what is hydrostatic work and how it is different from simple work, right? So there was a doubt whether hydrostatic work pertains to hydrostatic system or not. So what I was explaining in the previous session was right. All right. So the hydrostatic work is the work that pertains to hydrostatic system only. And the example for this, we can take any example of hydrostatic system, right? And then work can be done on the system and can be done by the system, right? So this particular topic of hydrostatic work, right? This you can find in another reference. So it is, so this is explicitly this topic has been explicitly covered in this particular reference, right? References can be referred to, right, for your doubts. Okay. So, okay, this way we come to the end of this session, right? We started with the topics that have been covered in week two of this course, right? So, those lectures were from lecture 4 to lecture 6. And then after that, we discussed conceptual questions, right? 17 conceptual questions we discussed based on the topics that have been covered in week 4 to week 6, right? So discussions were based on entropy, right? Entropy balance, entropy reversibility, Clausius inequality, Clausius theorem. So all these topics have been discussed in this session, and then in the next session, next section of this session, we discuss then numerical questions. So, in total, four numerical questions were solved based on entropy equations, right, and evaluation of entropy, right, right. And this way, we just proceeded in our this particular session, right, and. For this particular session, we shall uh, close this session for today. And for the next session, we shall meet again on Sunday with the same timing, that is 3 p.m. to 5 p.m. And till then, I'll say uh, thank you, right? And then happy learning, right? See you in the next session. Thank you.